Hello, chemists. Last week, we looked at hydrocarbons. You built a ton of models like this, right? And I took our models and I tried to build as big of a chain of hydrocarbons as I could with our model set. And the biggest I could make was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 carbons long. So this is the biggest chain of carbons we could make, 15 carbons long. And that is kind of like the same stuff that you'd find in like kerosene or jet fuel. Maybe diesel would have a couple of some of these molecules in it. But we're going to be looking at something a little because all of those things like gasoline and kerosene and jet fuel and diesel are all like a little bit too dangerous for me to send home with you. We will not be doing anything with any of those fuels, but we will be using a carbon that's even bigger. It's like 25, 30, maybe 40, so 20 lots of carbons, like 30 carbons in a row, so twice as big as this. So take a carbon chain that's twice as big as this and you'll end up with wax. So anyway, the bigger it gets, the more solid it becomes. You probably noticed that pattern. The smaller it is, the more likely it is to blow up and burn things, and be dangerous. So the bigger they get, the more likely they are that they are liquid. This one would be, like kerosene or diesel. Those are both liquid. And then as it gets twice as big as this, we end up with molecules that when they come together, they'll end up being a solid like this candle. So we're going to be looking at candle wax, which is, between 20 and 40, maybe 50 carbons. It can be, bigger than that even, but more than 20 carbons in a line and you'll end up with wax. Okay, let's look at how this candle actually works from a chemical standpoint. So when you light this candle, a lot of people think that, a lot of students have thought that the wick is what's burning. And it's true that it's the thing that looks black, right? It looks like, oh, it's burning, right? But it's not that the wick is burning. And you'll probably notice that you could burn this candle for like hours and that little teeny tiny wick does not go down. So, it is the candle wax that is the fuel that's actually burning, producing the flame. So the reaction is the candle wax burning with oxygen and producing the flame, producing the heat from that reaction. So let's look at what's actually happening. So when you light the candle, the wick is really good at pulling. Gotta watch my breathing on this thing. The wick is really good at pulling the melted wax. And if you look underneath the wick, there's going to be a little pool of melted wax. Got to talk over this way. There's a pool of melted wax underneath the candle. And that is, we're taking the wax, it's from being a solid to being a liquid. And then as it gets close to that bottom of that flame, it gets hot. It gets hotter than the liquid wax even. The liquid wax becomes a vapor, and the vapor is what is burning around that wick. The wick is pulling up the liquid, and it is turning into a gas, and the gas is igniting with the oxygen in the air, and then we have that little flame. Where the reaction is happening is in the flame. The flame is where it is the wax is reacting with the oxygen. And now there's a really awesome slow motion video that I linked in the instructions. I'd say go look at that, but I'm going to just show you quickly that what's actually burning is not the wax, solid wax, or the liquid wax. What we're actually burning is the gas, and we can actually see it if we put it out. You can light it off of the, Let's look at what happens chemically when we burn the wax in this candle. So we're going to be burning the wax or combusting the wax, and that's what the formula looks like. We're going to take a big long chain of carbons and hydrogens, right? In this case, we're going to look, and it's 25 carbons, 52 hydrogens all bound together in a big long chain. Now, like I said, this wax is a mixture of many different molecules. Some of them might have 30 carbons, some of them might have 40 carbons, some of them might have 42 carbons, some of them might have 23 carbons. So it's just a big mixture of things that are solid at room temperature. So wax is just these bigger molecules all jumbled together. So let's just we're going to take one example wax molecule and see what happens when we burn it with oxygen. Let me just show you what that looks like. An oxygen is O2, right? So here we've got this big giant molecule, C25H52, can't even fit it on the screen, right? So this is the C25H52 right here, big giant molecule. We burn it with oxygen, but we would need 38 of these things. Look at that, 38 O2s in order to burn all of those, break all those carbon bonds, break all those hydrogen bonds, break this whole molecule apart and have it join up with the oxygen. And then this is where that happens. That, remember with our salt reactions, we were seeing we took two elements, we react them together, and this is that reaction. When it happens, that's when we're seeing the flames and the changes. And that flame is when it changes into all of these carbons and hydrogens get broken apart, and the carbons get stuck to oxygens. You see the carbon gets stuck to oxygen, CO2, CO2, two oxygens and one carbon, two oxygens and one carbon is CO2. We're going to make 25 of these guys. Does that make sense though? Let's look back. There's 25 carbons in our wax molecule. Look, there's 25 carbons in all of those carbon dioxides. That fits. It's a balanced chemical equation. There's 25 carbons in the beginning and 25 carbons at the end. And we could check and see if the oxygens also have the same amount. I'm not going to do that right now, but we could also see if there's 52 hydrogens. That's a nice fun little puzzle for you. Check and see if there's 52 hydrogens in this reaction on both sides of this. And then we need 38 times 2 oxygens, whatever that is, 76 oxygens. So there should be a total of 76 oxygens over here. Fun little puzzle. So we've turned this big giant molecule into 25 of these and 26 of these. So this is a water molecule. You got the oxygen and then 2 hydrogens. You'd need 26 of these and 25 of those in order to break up this entire thing and burn it. And you'd be left with nothing but carbon and water. And now what I'd like to point out is I'm hoping you guys notice that this looks pretty familiar, right? Combustion of wax, you take a fuel, you react it with oxygen, and you end up with carbon dioxide and water. A lot of carbon dioxide and water, but still carbon dioxide and water. I'm hoping you've seen something like this before, probably in your biology class, if with any luck. So here we've got the combustion of glucose, right? You've seen this reaction in biology, I'm hoping. So we've got, this is glucose, 6 carbons, 12 hydrogens, and an oxygen all bound together in a ring. You look up the form, what it looks like. You saw when we did our molecules slides, you saw one of these guys. So there we go. We got a glucose, one little sugar molecule, and then it reacts with oxygen. Hey, oxygen. And then it makes carbon dioxide and water again. A different amount, right? But we could just double check. We could be like, oh, is the equation balanced? Look, there's 6 carbons here, 6 carbons there. The carbons are balanced. And I bet if you check, there is 12 hydrogens here. Ah, look, 2 times 6. And that would be, so for each water, there's 2 hydrogens, and then there's 6 of them. So that means that there's 12 total hydrogen over here. it is balanced. You can check the oxygens as well, and I'll just tell you, it's balanced. So that is, and notice they both make carbon dioxide and water, both of them. That's what happens. They both make the same thing. So you take a fuel, react it with oxygen, you end up with carbon dioxide and water. And let's look at one more. This is the combustion of fat or butter. I didn't have any sugar cubes. That would have been fun. But there we go. You take some butter and burn that. Same thing. Take some butter, burn it, and here's look at this crazy big molecule, right? There's a reason butter is solid, right? Here we got C55H104. That is a big molecule, hey? That is a big molecule. And then but you still burn it with oxygen, just a lot of them, and you end up with carbon dioxide and water again. A different amount, but you double check and you see, oh, 55 carbons, it's balanced again. So all of these combustions, the reason we do them is because we get energy out of them. We burn fuels to get energy. This would be almost the same exact reaction if I did hexane or octane from gasoline. Gasoline would be the same thing. You take a carbon and hydrogen molecule, burn it with some oxygen, you end up with some carbon dioxide and water. The only difference is how it gets balanced, these numbers in front. How many carbon dioxides and waters do you produce and how much oxygen do you need? That's the only difference. So all of these things, we're just burning them to get energy for fuel. So the reason we burn these things is for the energy. The whole point of fuels and food is so that we've got energy to live and do all the fun stuff we like to do with energy. So let's look at how we measure energy. Heat energy is measured in joules and calories. Joules is typically for physics and also for chemistry. We also use calories. Both of those are both used in physics and chemistry. But I know it's going to be trouble, and these are these things that I just hate, but sorry, nutritionists and chemists did not talk together enough in the 20th century. That's just, we are now stuck with one food calorie, or the big C, is the same as 100 calories with a little c. So I like to think of these as food calories or big calories, and these as like chemistry or physics calories. Like if you're actually measuring things in grams and that sort of thing. If you're not talking about food, we're talking about these kind of calories. So this is the chemist's calories, and this is the food calories. And it just is this way that whenever chemists or physicists are talking about calories, they're talking about these kind. And then whenever you're talking about food, like how many calories some food has in it, you could just multiply that by 1,000 and you'll end up with the calories that a physicist or a chemist would be talking about. Okay. All right. Well, anyway, that's confusing, but just so you don't get confused, like, oh my goodness, my food hardly has any calories in it. The amount of energy that is released by burning 1 gram of fuel is the heat of combustion. So does that make sense? The heat that you get from combustion, the heat of combustion is the energy you get by burning 1 gram of your fuel. And so let me just show you what that looks like. This right here is 1 gram of butter. So you kind of know what butter's like. And there's 1 little gram of butter. It's a little, about the size of my pinky. So we got 1 gram of butter here. I double checked on the nutrition label, and I figured out that 1 gram of this butter has 8 food calories in it. So this guy has 8 calories per gram. So this 1 gram has 8 calories in it. And then it also would be true that it would have 8,000 calories. And I know this, it's just the, you know, the little c, so big C versus little c. Anyway, 8,000 calories per gram. And it's also true that this particular thing right here has 8,000 calories, little calories, and 8 big calories in there. So now I ask you, you know, like, what if I had this? If you know the heat of combustion, you know how much is in 1 gram, you can easily multiply to find out how many calories are in something that is a lot bigger. So let me just do that quick calculation. How many calories are in here? We have 8,000 calories, little calories, per 1 gram. That's the heat of combustion of this butter, 8,000 calories in 1 gram. And then we want to know, but we know how much is in 1 gram, but we want to know how much is in this big stick of butter, which is 112 grams. And so we look at it, we go, okay, well, this is 112 gram, that's 1 gram. Let's just double check. Is it going to be bigger? Yes, it should be bigger. And let's just double check that we did the units right. Grams are on the top here, grams are on the bottom there, so they cancel out. I'm just left with calories. And so it's 8,000. So the top, multiply the top. So 8,000 times 112 is 896,000 little calories. And then the grams are canceled out and it's just a 1 at the bottom. So that's our answer. 896,000 calories in this stick of butter. And there's only 8,000 in that little gram. Okay. Okay, so now we've got your apparatus. We've talked all about fuels and how they work and that they produce energy when they combust. And we've talked about how much energy is in fuels, but we need to know how to measure it. Like, how do I know how much energy is in here? Well, what we're going to do is we're going to capture it. We're going to burn the candle and capture that heat in some water in this can. And so what you're going to do is you're going to take some water and put it in the can, and then the heat, let's make this so you guys can see it. The heat from the candle is going to go up into this can. And the nice thing is this can is aluminum, so it's really good at absorbing the heat and transferring it to the water inside the can. And we're going to get it nice and close. You know, I've got it, you know, I say to do like 3 centimeters. It could be even closer. 2 centimeters is fine. 2 to 3 centimeters from the top of the candle to the bottom of the can. You want it nice and close so the flame is just right on the bottom of the can. So what we're doing is we're capturing all that energy and putting it into the water in the can. And now if we could know how much energy the water absorbed, well, that would be great. And we do that, and I'll show you how to use this thing in a little bit. But you're going to take your temperature probe and put it inside of the can. And you can use it as a stir, that's fine. And this thing's pretty tough. As long as you don't get the, you know, be careful not to get the cord burned or any of the plastic parts. But this stainless steel thing is pretty tough. So you just keep track of the temperature of the water. And if you know just how much the water heats up, we'll know how much energy this candle put off. So I'm going to show you a little bit more about that. What is that? How do we use water to calculate heat? That's next. For this next part, we're going to look at how the water in your can, look at the calculations we're going to do with the water in the can. How does the energy, the heat energy that we're putting into the bottom of this can, heating up the water, how can we use that to calculate energy? And so we're going to start with I got to show you here, and then I'm going to do some calculations. But right here, I've got your 100 milliliter graduated cylinder filled up to 100 milliliters. So this is 100 milliliters of water. When you see this thing, it looks like this, 100 milliliters of water. And then I have your 10 milliliter graduated cylinder filled with, look at, it's so very small, just 1 milliliter of water. I could even prove it there. 1 milliliter water. You notice it is very, very small. 1 milliliter water here and 100 milliliters of water here. You notice this one's a lot smaller than that one. That's going to be important. So little 1 milliliter, 100 milliliters. We're going to look at those next. Okay, so let's look at these waters and see if we can do some calculations with it. We got the 100 milliliters here and the 1 milliliter here. Water is really cool because, and useful and ubiquitous, and chemists use it all the time. So water absorbs a lot of energy before it gets hot. It's one of the really special things about water. And it wouldn't, life on our earth wouldn't be the same without that property. So water absorbs a lot of energy. You can put a lot of energy in it before the temperature goes up very much. So it has a high specific heat capacity. That's what it means. Specific heat capacity just means how much energy can you put into it before it goes up. And let me just show you what that looks like. The specific heat capacity of water is the energy required to raise 1 gram of water 1 degree C. So how much energy do you have to put in to 1 gram of water to make it heat up 1 degree C? So I want you to think about it like this. If I took this tiny little 1 gram of water, it's 1 milliliter is the same as 1 gram. That's going to be important in your calculations. So water is really special that 1 milliliter of it also weighs 1 gram. There's a lot of these units are based around water, so it makes chemistry a lot easier. So 1 milliliter of water is also 1 gram. So I have 1 gram of water right here. If I heat it up, if I put a little lighter under it and I got it to heat up 1 degree C, there's a particular amount of energy it takes to do that. And that is the specific heat capacity of water. And the awesome thing about these units is, look, it's 1 calorie of energy. They defined it this way for water. 1 calorie of energy is what it takes to heat 1 gram of water 1 degree C. So if I want to heat it up 1 degree, I need 1 calorie of energy to heat this little bit up. So let's just see if we can use that. And to summarize that, it looks like this. 1 calorie per gram degree C. So you can see that 1 calorie of energy per 1 gram 1 degree C. So that's another way of writing that. So let's use that. Let's use that again. And we're going to take, we're going to say that we know that it takes 1 calorie to raise this up 1 degree C. How much energy would it take to raise this 100 grams 1 degree C? So we're going to say that we have 1 calorie per gram degree C, and we actually have 100 grams. And I'm going to clarify that. We have 100 milliliters in this graduated cylinder, but I've said that 1 milliliter of water equals 1 gram. That's how much it weighs. And that's not true for all of them, right? We looked at density and those are all different, but water, that is true at room temperature. So anyway, so we have 100 grams of water. And so let's see if we can cancel anything out. We can cancel the grams. And if we heat this up 1 degree C, then we know that it will take 100, 1 times 100, right, is 100. The units are calories. That's all that's left. The grams are gone. So I have 1 times 100 calories. And then there's nothing on the bottom. So that means all I'm left with is calories per degree C. So this will take 100 calories to raise it up 1 degree C. Well, what if I want to raise this large amount of water up 4 degrees C? How many calories will it take? Well, I'm going to say 4 degrees C. That'll cancel these guys out, right? And it will be 400 calories to raise it, to raise 100 grams, 4 degrees C. And I've used the units to help me get to that number. So does that make sense that it's going to take more energy, right? It takes 100 times as much energy to raise 100 times as much water as we started with. And it will also take 4 times more energy to raise it 4 times as high, 4 degrees higher. So yeah, that's that. That's how we use those. Okay, so now that we've got all of the theory out of way and the calculations, let's just show how in the world do we do this experiment. You've got your ring stand, you've got your little pop can held up here. Hopefully you've already practiced how to change your ring stand, like move this, or you can move this around to lower or make it higher. You really want to try to get it just right before you put your water in and before you start heating, because it gets harder to move it around after it's been heating some. So get it all set up so it's, 2 centimeters. What did I say? 2 or 3? Anyway, 2 is good. 2 or 3 centimeters from the top of the candle to the bottom of the Coke can. Try to get that candle right underneath the can. Get it all set up, and then you're going to want to take your 100 milliliters of water, and what you want to make sure is you want to read that thing, and it is important to actually get 100 point, or like at least you don't have to get it exactly 100.0, but you do need to read your scale. So if you have 98.6 milliliters, write that down. Make sure you try to read that thing. You only have to read it once. So just try to read it to the 10th of a milliliter. That means making an estimation between the lines. So you don't have to have it exactly 100, but you do need to read it and tell me exactly what you ended up with. Okay, so then you put the water into the can, pour the water into the can, all 99.3 milliliters or whatever it happens to be. Put all that into the can, and then you're going to want to set up your thermometer. And let me show you how to set up the thermometer. First, there's 2 parts. You've got this part, which is the actual temperature probe. And then you've got this funny Go Link thing. That's the interface that plugs, so that it makes this able to plug into your Chromebook. So what you're going to do is plug this into your Go Link. There we go. Plug that into your Go Link. And now this thing is getting ready to go into your can and just be there. And it can act as a stir. And now you've got this nice, woo, that's going to be fun. And then you've got, right. Maybe there's ways to make this work. So then it's really nice when you have more than one person doing this. This is the first time we've had to do it on your own, but hopefully you can figure it out. Then you've got this USB that's, part that's coming off of your Go Link. That's going to be your temperature, how to plug in your temperature thing to your Chromebook. Here's Vernier graphical analysis. And you notice once it pops up, it'll have this big graph. I think the graph is unnecessary. So let me show you how to get rid of the graph so you can actually get what you want. What you really want is this little measurement right down here right now. I would like to be able to see that better. That would be great. So what you're going to do is go up here. Yeah. So these little boxes, these 3 boxes, go up here to the 3 boxes. And instead of graph, get rid of the dumb graph. The graph is not worth it. And then put in meters. And then we end up with this nice big thing that says, what is the temperature right now to the 10th of a degree Celsius? And then you could just keep track of those numbers in your data table when you need it. You don't need to be watching the rest of it. So, and I like to make it even small, you know, make it small so it's not taking up my entire screen. You know, this meter can be this big, right? And now I can, you know, I've got all the rest of my screen. I can do all my other stuff, but I can keep track of my temperature there on my screen, and it's nice and big for me to see. And should be just working. If it says a temperature that doesn't make any sense, wow, it's cold in here, 17 degrees C. And then when you notice, it should change when I put my hand on it. Oh, look at it go. And it should get up to whatever it'll take a while to get to my body temperature because I have to heat up that thermometer, but that's how it works. And when I let go of it, it should go back down. If everything's working, that's how it should work. It'll take a little bit to cool down. Yeah. The tricky part now next after this, let's stop sharing because you've got this figured out. The tricky part about this deal is you're going to want to get cold water. So your 100 milliliters of water needs to start out pretty cold. It needs to be at least 10 degrees below room temperature. So figure out some way to make it cool. It was 17 degrees C. So you're going to want your water temperature should get cooled down to at least 7 degrees C if you were in my room. So I would want my water to be 7 degrees C because that's 10 degrees below room temperature. And then you're going to heat it up to, I would heat it up to 10 degrees above room temperature if I started there. So that's how you're going to do it. Figure out a way to cool it down. And once you get room temperature, then you're going to be putting your water into your cooled water into your can. And then you're going to put your thermometer into the can and get a cold water temperature. And then once you got all that cold water temperature figured out, then you light your candle and heat it up until it's at the at the goal temperature. Blow out the candle once it's at the goal temperature and wait for it to, it might heat up just a little bit longer. It'll take a little bit of time for it to get its highest temperature. And then once it reaches its highest temperature and starts coming back down, take that highest temperature you're able to reach, and that's the number you're going to want to use. All right.